But now we know how CO2 in the atmosphere goes into the aqueous phase and reacts with water to form carbonic acid. And it turns out that knowledge of that carbonic acid chemistry, which is referred to as the inorganic chemistry of water solutions, tells us many things. It allows us to calculate the pH of rainwater, which turns out, interestingly, to be acidic because of the uptake of that CO2 forming carbonic acid. But it also tells us how the ocean interacts with that CO2. And that tells us not only what's happening in the future as we put more and more CO2 in the atmosphere by virtue of burning fossil fuels, it also allows us to look back in time 10, 20, 30, 40 million years and map out why the carbon dioxide concentration in the atmosphere reduced from very high levels, around 1,000 parts per million, down to around 200 parts per million of CO2 in the atmosphere before the Industrial Revolution. And it allows us to examine how carbon dioxide controls climate by virtue of this carbonic acid chemistry that we have now dissected. So let's actually apply this to rainwater. It turns out to be a very, very interesting calculation. So we're going to look at a drop of rainwater, which is a drop of H2O, and we're going to look at the way the partial pressure of CO2 interacts to form carbonic acid, H2CO3, in the water droplet. But of course, the minute we see H2CO3 enter water, we recognize that it's going to dissociate first into the bicarb anion and second into the carbonate anion. And so we are interested in analyzing the concentration of every single one of these inorganic carbon species: the carbonic acid, the bicarb anion, the carbonate anion, and then of course we always want to keep our eye on the concentration of H plus and OH minus, because they determine the pH of the solution. Since we don't know the amount of dissolved inorganic carbon in a particular system, we need one more equation. But that one more equation turns out in its own right to be extremely interesting because it represents charge balance. And we know from our analysis of cations and anions how important the charge balance is. It's one of the most disciplined aspects of any chemical reaction. We always balance charge. So that means for our case that we have the H plus cation balancing all of the anions in that solution. Namely, we have OH minus, we've got the concentration of the bicarb anion and the concentration of the carbonate anion. That too corresponds to the fact that we have two negative charges on that carbonate anion. So we want to always make sure when we're doing a charge balance that we keep track of the positive and negative charges, because if we have two positive charges, that has to be multiplied by 2, just as two negative charges for an anion have to be corrected in the charge balance equation. We also know that we have the dissociation of water, which is equal to the concentration of H3O plus times OH minus, and particularly in carbonic acid chemistry, we always write H3O plus as H plus, so we have H plus times OH minus, and that is equal to our 10 to the minus 14. Okay, so we can rewrite the charge balance equation in terms of the pressure of CO2 and H plus. Now there's one little thing we need to watch out for, which is in the text, and that is the way in which the equilibrium constants are dealt with with respect to Henry's law. And in particular, we wrote, remember, that the equilibrium constant for the solution of carbonic acid in water was equal to the concentration of carbonic acid divided by the concentration of CO2 aqueous. And this is also helpful in reminding ourselves that we go from gas phase CO2 to aqueous CO2 to aqueous carbonic acid, and we always want to keep that in mind. Now, in our case previously, we have defined Henry's law as K prime for whatever species we happen to be looking at. So when we write these equations for the determination of the acidity in either rainwater or in the ocean, we want to remember that our KH, which we're going to use subsequently, is equal to our KH prime that we've talked about before, divided by this equilibrium constant for the conversion of CO2 aqueous to carbonic acid. So we're going to, from this point on, use KH without a superscript, and that is the relationship between that Henry's law constant and the one that we've used previously. Okay, so now we're ready to solve for our H plus concentration. That's equal to the dissociation constant for water divided by H plus the first acid dissociation constant for carbonic acid times the pressure of CO2 in the atmosphere divided by this Henry's law constant K sub H times the hydrogen ion concentration. And then we have one more term. That's the term representing our carbonate anion. And that term gives us 2 times the concentration of CO2 in the atmosphere times the first dissociation constant times the second dissociation constant divided by the Henry's law constant multiplied by the hydrogen ion concentration squared. We have made huge progress because we've got our key equation for calculating the H plus concentration in rainwater. And just gathering terms from the previous equation, we have H plus cubed is equal to the dissociation constant for water times H plus. And then we have the second term, which is the bicarb anion term. That's equal to K1 times the pressure of CO2 divided by the Henry's law constant times the concentration of H plus. And then we have the third term, which is the carbonate anion term. So our factor of 2 appears. Then we have the first acid dissociation constant, the second acid dissociation constant, multiplied by the pressure of CO2 in the atmosphere divided by Henry's law constant. Now, we can make a couple of approximations here because the carbonic acid solution, we've assumed that the concentration of OH is small. And we know that for a fact because it's an acid solution. And that means that the acidic component far outweighs the base contribution. Likewise, we know from the measured values of the first and second dissociation constant that the bicarb ion concentration is much larger than the carbonate concentration. And we know that because the acid dissociation constant for carbonic acid is much larger, that is forming the bicarb anion, is much larger than the reaction of the bicarb forming the carbonate anion. So that means that we can write the expression for H plus in this solution. It's equal to the first acid dissociation constant times the pressure of CO2 divided by Henry's law constant times the H plus concentration. Now we can simply rearrange, and we have the simple conclusion, because of the cancellation of terms, that the H plus concentration in rainwater is simply equal to the square root of the product of the first acid dissociation constant times the pressure of CO2 divided by Henry's law constant. That is a remarkable conclusion because it says that if we increase CO2 in the atmosphere, the H plus, the acidity in that rainwater, is going to increase as the square root of the pressure of CO2. And it also tells us something about what's going to happen in ocean water, because anytime we increase the CO2 concentration in the gas phase above the solution, it's going to increase the acidity within that solution. And as we'll see, the acidity in ocean water is extremely important for the biological systems that operate in the ocean.